Anyway, so I have given idea on first problem. Now you solve me and tell me the solution. Okay, wait, open it. हाँ, आ गया ये ओपन हो गया. खोल देते हैं. हाँ, जो लिखा है अब इसके बाद बोलो. What will be your function? For first problem, so a connected diagonal of space having more than one point has greater than equal to C point. So I've given a construction, and we see that by using the definition of completely regularness, means the space is completely regular, we can have a function f which has the property that fx is equal to 0 and it's 1 outside. Right? So using this, we have proved that the entire interval 0, 1 is lying inside the image of x, means 0, 1, the closed interval is successive efficient. From here, we can directly say that this cardinality of x is strictly greater than equal to C. But for the second problem, you had a connected space, means a connected separable metric space, and it claims that it has either 1 or C number of points, means it will be either a singleton set or the number of element in that space will be same as the cardinality of R or the continuum cardinality. I've given the proof that whenever it is connected, then cardinality of x is at least C. So it was done during we did it few minutes ago. Where is the option for editing? I don't know. Fine. So we have proved that this space X, whenever it is completely, whenever it is connected, then connected metric space, then cardinality of X is greater than equal to cardinality of, or cardinality of X greater than equal to C. Now our aim is to prove that this C is less than equal to cardinality of X, right? So now by the hypothesis, the space is separable. We have assumed that B has a countable dense subset, and let's say the elements of BR looks like A1, A2 up to AN. Now for each x belongs to X, we define a function f as fx is equal to this tuple. This is an element from R infinity, okay, or you can say R power n. Our aim is to prove that this function f is injective. This f is injective. Can you quickly try this? Why this function is injective? What do you mean by injective? You mean if x not equal to y, then fx not equal to fy. You have to prove this one. Can you take 5 minutes and try whether you can prove this one, that if x not equal to y, then fx not equal to fy? Please. Okay. So suppose x and y belongs to X, we have suppose for x and y belongs to X, with x not equal to y, we have fx equal to fy. Then what is the meaning? This means, what is that? This means
dxa.
dx comma dxai, right? Same as dyai, right? For all I belongs to n, right? This holds. Now dxi is equal to dyai. Now you see this x and y are not same. So therefore d of x comma y is strictly positive. Fine.
Yes, sir.
Now if you consider this neighborhood, say let's say if you consider the set element x, and if you consider this neighborhood x comma dxy by 2, you consider this neighborhood. This is the neighborhood of x, right? A neighborhood of x, and you are given that your set B is dense in x. Dense in x. So this is a neighborhood of small x, and your B is dense in x. So from these two, what you can say?
Their intersection non-empty.
Yes. Therefore, B intersection this ball x comma dxy by 2 is non-empty, right? Means there exists some aj, say, belongs to this set, right? Means belongs to bx comma dxy by 2, right? Again, I am doing this because I need pages. Okay, so we will see later on this problem. So now what you have? You have dx comma aj equal to dy comma aj, right? And by this one, and we have aj belongs to the ball x comma dxy by 2. So from here what you can say, what is dx comma aj? Can you say anything about this element, this quantity?
Less than dxy by 2.
Yes, strictly less than dxy by 2. Now you see dx comma y. What is triangular inequality? Dx comma aj plus daj comma y, right?
Yes, sir.
But these two are same. So this is equal to 2 times dx comma aj, which is strictly less than by this inequality dx comma y 2 times by 2 is equal to dx comma y. So what we got is that d of x comma y is strictly less than dx comma y. This is not possible, right? Because this implies 1 less than 1. So how it can be true? So therefore this is not true, means if we take x not equal to y, then we must have fx not equal to fy. Fine. Therefore the function f is injective. Fine. Whenever f is injective, that means this space you have function f from x to r power n, and this is the injective function. What does it mean? So f is injective. This implies what? Cardinality of x is less than equal to cardinality of r power n, right? If f is injective, then x will be means this Rn, r power n will contain a copy of x. That means, in other words, you can say x is subset of r power n, taken over the action of it, and therefore the cardinality of x is strictly less than or less than equal to this. This is same as c. So earlier we had c is less than equal to cardinality of x, and now we have proved that c less than cardinality of x is equal to c. Therefore, what we can say? Yeah, take this. Therefore, cardinality of X equal to C. Fine. So this proof is not that much difficult, but you have to find out the right track. How you can solve this one? Okay. Fine. So maybe this one I will come up with this problem little later. Let me solve this problem. Before that, I should erase this one. Is there anything to delete? Anyway, so maybe we can move to the next. Can start from the next page, I think. Okay. Fine. Look at this one. You should tell me the solution, answer. The solution, you should tell me the answer. Okay. So what about this one? X is equal to R and Rn, whether they are homeomorphic. Are they homeomorphic, R and Rn? Are they homeomorphic?
No, sir.
Why? Make one more copy. I think I should use this one. Why R and Rn are not homeomorphic? Why Rn are not homeomorphic? Tell me.
Sir, R is connected, Rn is not connected.
Rn is not connected.
No, Rn is connected for all and
Oh, Rn is not connected.
yes, sir, Rn is
Who is
connected.
that? Anyway, so Rn is connected. So why then why they are not homeomorphic? Okay. So you have what is R minus 0? See, let me tell you. You had an exercise or you had a problem in your minor exam, right? If X and Y are homeomorphic, implies X minus say A and Y minus FA are homeomorphic, right? Right? Just you can just take means say if F from X to Y is the homeomorphism. So if F from X to Y is the homeomorphism, you just take the restriction X minus A. So this is the map from X minus this set A to Y minus F. So this will give you the homeomorphism between X minus A and Y minus F. Right? Now you see x equal to r and y equal to rn. If they are homeomorphic, if x and y are homeomorphic, then for any times a of r or any real numbers, in particular for 0, you can say that r minus 0 and rn minus f0. They are also homeomorphic, right? But are they homeomorphic? Tell me, is it connected?
No, sir.
Why?
Sir, it is minus infinity comma 0 open and 0 to infinity, and तो यहाँ पे दोनों ओपन सेट है और नॉन इम्पटी इंटरसेक्शन है तो कनेक्टेड
Minus
तो
infinity comma 0 union 0 comma infinity, right? Therefore r minus 0 is not connected, but this is connected. Why? Why rn minus a single point is connected? See, Rn minus a single point is again homeomorphic to Rn minus 0, right? The 0 element, 0, 0 up to 0, where 0 is an n tuple, right? Now this is in fact path connected. This is in fact path connected. Okay. So if you remove, in fact, if you remove a point, say, if you say take an element x from Rn minus 0, here 0 means 0 element, and you can say y belongs to Rn minus 0. Okay. So, and x not equal to y. Now you take the line segment joining x minus y. So what is the line segment? It is tx plus 1 minus ty, where 0 less than equal to t less than equal to 1. Okay. So this point will lie in Rn minus 0, provided that this is not equal to 0. So if this assume 0, means if 0 belongs to this line, then this line segment will not be there. But unless if 0 is not here, then this line segment will lie completely inside Rn minus 0. Is it clear? No, it's not clear. Let me, you know something called polygonal connected, right? Suppose you have here R, okay, you have here R. Look at the picture. This is your 0, and therefore this is your R minus 0. Here it is minus infinity is here, and plus infinity is here. Okay, it's from here, not from here. So let me. Okay, this side is minus infinity comma 0, and this side is 0 comma infinity. Now you look at this one. Now it is your R2 minus 0. Fine. Now you take, my claim is this is path connected. See, these are the techniques to prove that this space is path connected. This will be useful in your future as well. Okay. In fact, you can get some problems from here also. Okay. So now you take 2 points. One is from here, and this is say your x, and this is say your y. Right? Now you consider this same. This is actually the path joining x and y. Right? You consider the path joining x and y. Does this path lies inside R2 minus 0? Yes?
Yes, sir.
So this point lies in R2 minus 0 because this line does not intersect the origin. But what if we take a point y from here and then we consider this line? Can we say in this case the space is path connected? means the line still lies inside R2 minus 0 because yes.
लेकिन अगर पाथ कनेक्टेड शो करना है तो लाइन से क्यों देख रहे हैं हम?
हाँ, वो तो पूछ रहा हूँ कि पाथ कनेक्टेड तो लाइन क्यों देख रहे हैं? मैं एक्चुअली आई एम ट्राइंग टू गिव ए पाथ बिटवीन x and y.
Yes sir.
And actually this kind of path will work whenever this line does not intersect the origin. But since this line intersects the origin, so this kind of line, in this case, it will not work. To work with this kind of lines, you need to take another point. Say another point, say Z from here. Now you join the line segment YZ and ZX. Okay, and so you have a path from X to Y. हाँ, अभी तुम्हारा ये क्वेश्चन है कि अगर कोई भी एक पाथ दे देंगे, कोई भी एक कर्व दे देंगे तो हो जाएगा, तो लाइन क्यों दे रहे? एक्चुअली टेकिंग लाइंस आर रिलेटिवली इजी देन टेकिंग एनी अदर पाथ्स. Okay, so whenever you feel that using these lines are applicable, to use lines because the calculation or you can visualize them very easily. But of course in a linear space, but if your space is some abstract and if you are trying to keep some abstract path, but this is not that much trivial, right? So working with lines are relatively easier. That's why I am giving lines here. So this is actually in fact polygonal connected. Polygonal connectedness have been used here. Okay, fine. So it's clear that why R and R power n are not homeomorphic. Second one, where are the homeomorphic 0 infinity and R?
सर ये भी नहीं होगा.
Remember 0 infinity and R. Are the homeomorphic? क्यों नहीं होगा?
सर इसमें भी R minus F0 डिफाइन कर.
R minus
0 disconnected, but 0 infinity is disconnected.
R minus 0 disconnected and 0 infinity connected, right? Actually
R minus F0.
R minus F0, because if F from here to infinity to R is the homeomorphism, then if you consider this set 0 comma infinity, this is connected, but R minus F0 is disconnected. So therefore they are not homeomorphic. Fine, good. What about third one? I taught this problem in class, so tell me, what about this one? Try to visualize through graph first. Okay, you have the line segment 0, 1 and you have the circle. This not looks like circle, but in fact this is circle for us. Okay, tell me whether they're homeomorphic or not. Are they homeomorphic?
No sir.
Why? We take a point from here. Yes, circle में
सर्कल में से एक पॉइंट डिलीट कर देंगे तो फिर भी वो कनेक्टेड रहेगा.
डिस्कनेक्टेड रहेगा, बट ये डिस्कनेक्टेड हो जाएगा. Therefore they are not homeomorphic. Fine. And the last one is S1 and Sn. What about S1 and Sn? So now fourth one, S1 and Sn. What about this one? Again, you consider this is S1, you consider some Sn. Anyway, okay, so say this is our Sn. Okay, so don't bother about those. You know something called stereographic projection, right?
Yes.
Do you know that?
Yes sir.
Are you all know those, that stereographic projection? What you take, you fix your north pole, right? You fix your north pole and take the line segment from north pole to Where? You take a point from this sphere and you join the line through North Pole to that sphere like this. Okay, and then you see that whenever you delete your North Pole, you find that your space is homeomorphic to Rn, right? In fact, you can say Sn minus 1 or Sn minus 1 means the North Pole is homeomorphic to Rn like this. Okay. So now if you delete one point from here, it will be homeomorphic to 0, 1, means it will be homeomorphic to say R, and here it is homeomorphic to Rn. So they are not again homeomorphic, therefore it's easy. Fine. Actually, in algebraic topology, there is something called homology theory. Okay, something called homology theory. Here we have just distinguished between S1 and Sn. Okay, let me complete this one first. S1 and Sn. See, if you delete one point from S1 and delete one point from Sn. Okay, now since still these two spaces are connected, and if S1 and Sn are homeomorphic, then Sn minus one point and Sn minus again Sn minus that point will again homeomorphic, right? Now we delete another point. In that case, say S1 minus 2 points, say 1 and 1 is your north pole and S is your south pole. If you delete these 2 points, you will see that the spaces become disconnected. You will have two connected components. But in fact, if you remove 1 point from here and 1 point from here, means 2 points from Sn, it will still connected. Okay. And in this case, therefore, S1 and Sn are not homeomorphic. Now, using these connectedness kind of things, you can work with S1, you can distinguish between S1 and Sn. But what if your spaces are say Sm and Sn? Then how do you distinguish them? Actually, the tools, whatever tools you have in your hands from this course, those may not able to provide the solution of this problem. Or in fact, even if they are able to provide, this will be very difficult. In algebraic topology, we actually deals with this kind of problems using a homology theory, or in fact, homology group. Okay. And there we see that we define a certain kind of groups, and we see that whenever two spaces are homeomorphic, then their homology groups are isomorphic in terms of some group theoretic structure. And we see that in homology groups, the nth, if we calculate the homology group of Sm and Sn, actually in m-dimensional space, in mth homology group, these two are not same. That's why they are not homeomorphic, because the homeomorphic spaces has the same homology group. That's why. But since in this case they are not same, means they are not isomorphic, therefore they cannot be homeomorphic. So actually we deals with the homology spaces actually. Fine. In fact, using these, we distinguish between Rn and Rm. Okay. So these are not homeomorphic, can also be proved using this kind of spaces. So actually what we see, we first assume that suppose these two are homeomorphic, say Rn and Rm are homeomorphic. Now we delete one point from each space, say Rn minus say A, then Rm minus B. So these two again will be homeomorphic. But there is something called deformation retraction. So this space will deformation retract to Sn minus 1, and this space will deformation retract to Sm minus 1. Now Sn minus 1 and Sm minus 1 are homeomorphic provided m minus 1 equal to n minus 1. Therefore, Rn and Rm are homeomorphic provided m equal to n. That's how we use homology theory there. Okay, anyway, forget about this, whatever I told you. Whatever I
सर ये कैसे कि Rn minus A is isomorphic to Sn minus 1?
not isomorphism. See, there is something called retraction, deformation retraction. Okay, deformation retraction. Okay, not isomorphic, not homeomorphic, not isomorphic. There is something called deformation retraction, and in this case, deformation retraction preserves the homology groups, and that is why they are preserved. Okay, actually, these are all parts of homology theory, and you will not understand those in this moment. But I told you just to give you some motivation from algebraic topology. That's it. Now forget about this one. Okay, forget about this one at the moment. Okay. Now this is very easy problem. So every continuous function. Any continuous function has a fixed point. F from 0, 1 to 0, 1, 0, 1 to 0, 1 has a fixed point. So how do you prove? We use or any other who is there? Bolo.
So define a new function gx equal to fx minus x.
Oh, good. Gx equal to fx minus x. Then
we know that f function is 0, 1 to 0, 1. Then we know that f0 and f1 is less or equal to 1 and greater or equal to 0. From there we can use IVP, means intermediate value theorem.
वो तो IVP हो गया. Now use connectedness. Use connectedness of 0, 1. IVP में भी connectedness property है, पता है तुम्हें?
Yes sir, interval पे apply करते हैं ना.
हाँ, interval, right? Used by this argument, okay, using IVP also. But try to say whether they are try to give some argument so that it contradicts the connectedness of this interval. For say, you consider gx is equal to this, you assume that fx is not equal to x for all x belongs to 0, 1. You now consider a set all x from 0, 1 such that gx greater than 0. And V you consider the set element x belongs to 0, 1 such that gx less than 0. These two are open sets, right? And you can write your interval 0, 1 as U union V, right? And therefore you have disjoint, means this is called separation. Therefore, whenever if fx not equal to x for all x belongs to 0, 1, then you have a separation of this interval 0, 1 in terms of open sets. So therefore it has a fixed point, right? What about second one? This is again very easy from algebra, right? Polynomial of a degree has at least one real root. Bolo, how to prove polynomial of a degree? Okay. Can you solve this one? Shall I leave it for you?
Yes.
But make sure that you need to verify two things. Okay, actually you need to use the condition that R is connected. You consider your polynomial as a function from R to R, okay, by taking the value P of R, or yeah, by taking just the values PR, or R goes to PR. Okay, you have to find out two elements A and B. Find, I am giving you hints. Find two elements A and B such that P of A is greater than 0 and P of B is less than 0. Okay, so then what you will have is that you have P, if you consider PB and PA, Now see, PR is connected subset of R, and therefore PR is an interval. This implies PR is an interval which contains PB and PA. Therefore, this PB comma PA, this will subset of PR, right? But this is negative, this is positive. In fact, 0 belongs to here. So 0 belongs to PR. PR means image of the image of P. So therefore, there exists some x belongs to R with Px equal to 0. So all you need to find out A and B where PA is positive and PB is negative. Can you do that? Okay. I am giving you a hint for greater than 0. If your polynomial is like this, if your polynomial is x to the power n plus a n minus 1 x to the power n minus 1 up to a0, where n is odd, given odd degree polynomial. Okay, in this case, you try to you may take say your a as, or in fact we can say alpha as 1 plus a n minus 1 plus up to plus a0. Try to take this alpha and see. Okay. Try to say take this alpha is equal to this element 1 plus mod a n minus 1 up to mod a0 and see whether this is positive, strictly positive. This is not easy. Okay, it will need a lot of words. It looks like easy, but it's not that much easy. Anyway, I'll leave it for you to verify. And once you find out this alpha, you will automatically get some B for which that PB is strictly less than 0. Okay? Fine. So clear? Try to work with this alpha. Okay? Are you in the class? Are you listening me? Are you following me? I don't know.
Yes, sir.
अब इसमें बोलो बस अभी 5 मिनट का काम है उसके बाद छुट्टी ठीक है So now find all the homeomorphic classes in the following spaces. So these are actually subspace of R2. Okay, just this kind of images you have. Tell me which spaces are homeomorphic. Okay, so first take C
And I,
then
J,
J,
L.
L,
No, sir. Maybe L. Not
L,
sure.
yes, L, then
U, S,
U, S, and V, what about V?
सर अगर L है तो V भी हो जाएगा.
हाँ, L जो है तो V भी हो जाएगा. E, Z, what about Z?
No, sir.
Y? Y Z is not homomorphic to I.
सर वैसे सर ये है क्या मुझे समझ ही नहीं आया.
ये they are homeomorphic. Homeomorphic क्यों नहीं है?
मतलब ये तो मतलब क्या समझ नहीं आता कुछ.
Actually
बस पिक्चर्स है और इनमें बताना कि होमोमॉर्फिक
हो सकता है तो ऐसे बताना है. Okay, try to think about this. Okay, this is very interesting. Whenever you get time, you try to find out that which spaces are homeomorphic. Okay. In fact, Z is also homeomorphic to this one. And what else? M, N. These are also homeomorphic to that. Where is G? G is also homeomorphic to that. Actually,
W भी बोल सकते हैं.
W is also homeomorphic. Actually, you can see those are nothing but lines. So you start with this line, this line, okay, including the endpoints. And what is your J? Your J is containing this line. Now ये J क्या है? इसको बस ऐसे सीधा कर दो. ठीक है. तुम्हारे पास एक रोप है. रोप तो मेरे पास नहीं है अभी. चलो रोप नहीं है, रोप से नहीं दिखा सकते. तो दिखा दे. ठीक है.
सर फिंगर से दिखा सकते.
हाँ.
फिंगर से दिखा सकते.
हाँ, फिंगर से दिखा सकता है. थैंक यू. ये है क्या? ये हो गया मेरा ये फिंगर देखो. ये हो गया तुम्हारा आई. ठीक है. और ये हो गया एल. ये फिंगर से अच्छा नहीं होता. रोप को तो सीधा कर सकते हो ना. एक सेकेंड रुको, मैं रोप लेकर आता हूँ. Can you see this one? Yes?
Yes, sir.
हाँ.
Yes, sir. Yes.
ये क्या हो गया? ये आई है ना. अब now you can now अब इसको थोड़ा सा बैंड करो. ऐसे थोड़ा सा बैंड करो. क्या बन जाएगा? ये मेरा हाथ में देखो. क्या बन गया? जे बन गया ना.
Yes, sir.
इस तरफ आएगा, ये इस तरफ आएगा. जे तो मेरे साइड से इस तरफ है, तो मेरे साइड से इस तरफ आएगा. जी मेरे तरफ से तो इस तरफ आ रहा है. I don't know whether they show the mirror image of the same.
Yes, sir.
ये हो गए. अब देखो एज देखो. ये हो गया फ्रंट. सेम स्पेस. ठीक है. सेम स्पेस. ये हो गया तुम्हारा फ्रंट. ये देखो एस हो गया.
Yes, sir. S हो गया.
एस हो गया ना.
Yes, sir.
अब क्या है? भी बनाना. ये देखो भी बन गया.
V बन गया. U भी बन जाएगा.
बन गया. अब इसको थोड़ा सा और कर दो.
W बन जाएगा.
W बन गया. और W को उल्टा कर दो. क्या बन गया? M बन गया.
और सर O भी तो बन जाएगा.
हाँ.
O.
नहीं, जब O बनेगा तब
O नहीं बनेगा.
तो ये एंड पॉइंट्स को आइडेंटिफाई करना है ना. अच्छा ठीक. हाँ ये O बन गया है. एक्चुअली यहाँ पे देखो, अगर तुम ये O है. ठीक है. अगर तुम O से एक पॉइंट डिलीट करोगे तो क्या रहेगा? ये स्टिल कनेक्टेड होगा. But if you delete one point from I, then it will be disconnected. It will have two connected components. Therefore, O and I are not homomorphic, right? हाँ. अब देखो, इसको देखो. D के साथ और कौन है?
P.
D के साथ P नहीं है. D के साथ एक और है. D के साथ कौन है?
B हो जाएगा. B.
D के साथ B भी नहीं होगा. B तो फिगर 8 है.
सर O हो जाएगा.
हाँ, D के साथ O होगा. ये कौन है? थैंक यू. गुड, वेरी गुड. D के साथ O होगा. ठीक है. These two spaces are homomorphic. फाइन. अब देखो A देखो. ये तुम्हारा हो गया तुम्हारा A एंड ये हो गया तुम्हारा R. Are they homomorphic?
Yes, sir.
Yes, sir.
बस वो करना है. Therefore, A and R are homomorphic. But P, A and R are not homomorphic. Means P and A are not homomorphic. Okay. P and Q are not homomorphic. See, these spaces are this space and this space. They are in different connected components. Okay. And A and R. Use this color, this A and R. Okay. A and R लिख दिया. P same. P itself homomorphic. P is homomorphic to none of the spaces. Okay. Similarly, you can prove that Q is homomorphic to none of the above mentioned spaces, none of the others. Okay. and you have the big class, this one, C I में ऊपर वाला पार्ट नहीं है, अगर ऊपर वाला पार्ट होगा तो वो डिफरेंस स्पेस बन जाएगा, सिर्फ दिस वाला लाइन, ओके, ओनली दिस लाइन, I J L M N and then S U V W Z. Okay. Now अब देखो B की क्लास में भी कोई नहीं है, राइट? फाइन।
सर इसमें जी नहीं होगा?
उसमें हाँ, इसमें जी भी होगा, थैंक यू। इसमें जी भी है, कौन बोला ये? जे एल, आई से पहले यहाँ पे जी है, ये जी तो इस टाइप का नहीं है, जी डिफरेंट टाइप का जी है, ठीक है? बस ऐसे आ गया, ये कैसे आ गया? हाँ, मतलब जी भी है ये क्लास में, ये जी डिफरेंट हो गया, ये रोने लायक हो गया, ये दिस काइंड, ओके, ये जी हो गया। नाउ यू कंसिडर, और क्या बाकी है? ई, आर ई एन एक होमोमॉर्फिक, ई का ये जो डंडा है ना, इसको उस पर सीधा कर दो, सीधा कर दो, तो ये बन गया एफ, है ना? therefore E and F are homeomorphic. So E, F. What about T? T same, right? ये जो F का है, F का इसको सीधा कर दो तो T बन गया T. What about Y? Y also, right?
Y also.
Yes. So Y also. Okay. So is there anything left? X. Actually, what we check is that we check the connectedness. We first take an element from here and try and say we are checking the homeomorphism between whether the space A and I are homeomorphic. Fine. So let's do that. You take a point from here, say this point. If you delete a point from here, then it will produce two connected components, right? So from here as well. In fact, if you consider a point from here, it will produce how many connected components? It will produce two connected components.
Sir, where are you writing?
I'm not writing, I'm just saying. Okay, it's for understanding actually. And this is actually, I don't think it will come in their exam, but whenever you are studying connectedness, you should know this, you can face this kind of problems. In fact, this kind of problems also asked in CSI, NET, and in fact in GATE exam also. Okay, so that's why I told you. It's up to you, how do you verify whether this is homomorphic, but I am saying that if you delete a point, if you delete this point from A, your space will be contain this one and this kind of two components. If you delete from I, it will be of these two components. So first one and second one. Now it has two components and it has two components. So being a homeomorphism, this component will homomorphic to one of them and this component will homomorphic to other. But this is same as shape, this kind of shape, the kind of shape, but this is same as I, so therefore they cannot be homomorphic. Okay, you have to use this kind of logics. And even in fact for the others also. You can see here X. Say look at X and say B, X and A. Okay. If you remove this point of intersection, if you remove so if you remove this point, from X, then it will produce 4 components, right? 4 connected components. The components are these, and this, right? But if you delete any point from A, it can give you at most 2 connected components. Therefore, they cannot be homeomorphic. In fact, for any other spaces, you can say if you delete, okay, if you delete a point here from here, the space will still be connected. But if you delete a point from here, you will have your B is like this. If you delete a point from here, your space will be like this one and this one. Okay. Therefore, it has 2 connected components, but X has 4 connected components. Therefore, X and B are not homeomorphic. Using this kind of arguments, you have to prove. Okay.
So, what about H and K?
H and K are homeomorphic. Where H and K? You can see this is your H, right? This is your H, and where is your K? Your K is this one. This is same as this is like this, and from here it is that. Just इसको थोड़ा वो कर दो, सीधा कर दो हो जाए, right? So this may make this line straight, so it will be this, and therefore the homeomorphic. That's it. H and K are homeomorphic. Okay. Means from here, by looking at the spaces, you can say whether they are homeomorphic. There are plenty of exercises. There are plenty of theoretical arguments where one can work with, like using homotopy theory, homology theory whenever you study algebraic topology. So in that case, there you will see whether there are more arguments that the spaces are not homeomorphic and all those. Anyway, so I don't think sir will ask this kind of problems, but of course he can ask anything. And again, please try to follow the instruction or try to follow the suggestions which he has given during the classes. And he also mentioned that there will be more than 30 marks question from connectedness, compactness, and I think he has mentioned 4 or 5 kind of topics, like Argyll-Ascoli theorem and Stone-Eustace theorem and all those. So if you study well from there, you can also get marks. So it's not a problem. Anyway, and I can say that one more thing. I think around 42 students has dropped from this course. Withdrawn means they have withdrawn the course. I don't know why. That told many students to withdraw, but when there are students who got more marks, even more than 20, means students who got 20 plus, they have also withdrawn from the course. I don't know what is their issue. Anyway, one more thing.